So I will mute myself, I guess, or doing it.
So did you get a second DNP machine yet?
We just got the Klystron. So the Klystron is coming in 1 month. We will try on the 400. So we got the 400, and then with a Klystron that will be delivered in 1 month. So that would be nice.
So you have a 600 now too, though.
Well, 600 we have with Geotron, and 400 will be with Klystron. We wanted to go to lower field because we do a lot of platinum NMR, you know, with Aaron and Anne, and 600 doesn't really help with platinum NMR. The CSAs are much larger, and so this is sometimes it's good to go to lower field, as you know.
Oh, you just spin faster.
Yes,
so.
Yeah, that's what we do also with Aaron, but still, platinum CSA and the metal CSA are pretty high. And anyway, we have Sanders. If you want to go to very high field, I hope soon he will get his big boys working. So.
You mean Xander is?
Yes, Xander. Yeah. So.
So he's building an 800 or
I think it's really something like that. Yes, I don't know. I have not seen yet the machine. So.
Well, yeah. Now spinning fast at high fields is important. So yeah, I'm gonna answer my phone here just a second. Cortec Net is trying to sell me rotors.
Huh? Okay.
That was Cortec Net. Yeah.
Philip Kokos or?
Huh?
Okay. Yeah.
Was it Philippe?
Yeah, exactly. Was it Philip Kokos?
Yeah, it sounded like it.
Okay.
Why don't we get going, Kong? All right. Okay.
Yeah. Yeah. Just give me 1 minute. Let me try to. Okay, let's get going. So good morning, afternoon, or evening, wherever you are. Welcome back to our ZOOMinar again. I've not done this for a long time, but I guess quite many of you have been listening to our series for quite long. But anyway, I will just like put the information in the chat room again in case that you're not aware of this. So we have a mailing list which we use to regularly distribute information about our upcoming talks. And also we have the recordings of our past sessions available if you go to the SSNMR DNP ZOOMinar website, of which the link is given in the chat. And then if you have any questions, you can just like put the questions directly in the Q&A instead of the chat, and then I will read the question and then deliver it to the speakers today. So today we have two excellent speakers. So the first one is Dr. Daphna Shimon, and then which I will introduce, and the second is Professor Christophe Copéret from ETH, and then of which Bob will introduce later. So let me just yeah. So Daphna started her undergrad in Tel Aviv University. After that, she went on to do a PhD with Shimon Vega at Weizmann Institute. And then after that, then she went on and to do several postdocs. And the first one is at Washington University of St. Louis. And then after that, she went on for a second postdoc at Dartmouth College. And then now, if I'm not mistaken, she's beginning as she started an independent research group at Hebrew University of Jerusalem. And the title of her talk today is Large Room Temperature Bulk DNP of 13C via P1 centers in diamond, of which I assume this is something that she did during her postdoc at Dartmouth, if I'm not mistaken. Anyway, so let's, Daphna, the stage is yours, and we are interested to listen to see what you have to share with us. Please.
Thank you. Thanks a lot. And thanks to thank you for the introduction. Okay, I think the slides are working out. Yeah, so this is work that I started during my postdoc at Dartmouth with Shaker Manhattan, and we've been working on it long distance since then, and now I'm at the Hebrew University. So I'll be talking about DNP of carbon-13 in diamonds using P1 centers as the electron for the polarization. So I think everyone or most of you have heard of NV centers in diamonds, where there's a substitutional nitrogen instead of one of the carbons, and then next to the nitrogen is a vacancy, a missing carbon, and that's the NV center. And these have spin 1 electrons. And the good thing about NV centers is they have very long relaxation times, electron relaxation times, decoherence times, and also you can access them using optical pumping and optical detection. And so NV centers are really good for applications of single spins and for hyperpolarization. The problem with NV centers is that the polarization depends on the angle of the NV center with respect to the magnetic field. And so sometimes it's difficult to polarize at high field, and especially powders. And so that's where P1 centers have a bit of an advantage. And so P1 center is just a substitutional nitrogen. You don't need a vacancy nearby, just a nitrogen instead of a carbon. And so that results in a spin half electron. The relaxation times are still long, but you can't access it with optics. The good thing about P1 centers is that the concentrations are much higher than NV centers, and so they're just much more common, and they're very useful for room temperature enhancements and also in powders. And so in general, diamonds have a lot of potential applications, such as medical imaging. You can use them for tracers because they're non-toxic. For microfluidics, you can imagine that if you had a diamond surface, you could polarize liquid as it's moving across the surface. For quantum computing, of course, with single spins, with long decoherence times, that's the thing that everyone's looking for. And also for magnetic field measurement. And here's like an example of an NV spin on the surface of a diamond. And if you place another molecule on top of it, you can try and detect the spins from that molecule using the NV center. That's the kind of things people are envisioning. But today I'm going to be talking about the P1 centers. And here you can see DNP enhancement of carbon in a diamond powder. The powder is 15 to 25 micrometer in diameter, and the concentration of the P1 center is about 120 ppm. Everything is natural abundance, and we're working at 3.4 Tesla, which is about 94 gigahertz for the electron and about 36 megahertz for the carbon. So all these experiments that I'll show you are room temperature without magic angle spinning. The setup is pretty easy to build for yourself, and because of the long relaxation time, I only worked at 120 seconds and or about 300 seconds and not much longer than that. So, of course, in DNP, the first thing that I do after checking the enhancement, or even before that, is measure the DNP spectrum, which is the DNP enhancement as a function of the microwave irradiation frequency. And here, when you look at the carbon DNP spectrum, there's just really a lot of things happening. There are a lot of features, and it's not fully obvious when you look at it what's going on. So the best way to decide what's going on is to measure the EPR line. And so we worked with Susumu Takahashi at USC, and they measured the EPR line of the diamond powder at room temperature at high field 230 gigahertz. And you can see that the EPR line is split into three. It's basically a spin half electron split by the spin one nucleus of the nitrogen, N14. And so there are three manifolds, each one for the different N14 spin state. And we can fit the EPR line with easy spin and then convert it to 94 gigahertz, which is the field that we did our experiments on. And so here you can see the comparison between the DNP spectrum and EPR line. And maybe when we look at this, it helps us a little bit understand maybe the DNP spectrum, but it's still not fully obvious that what exactly we're looking at. It's not clear right away. So in the literature, if you look for similar types of diamond powders, there's this really nice paper by Christian Brettschneider and Lucio Friedman, and they did DNP of carbon in diamond powders at low temperatures, 1.65 Kelvin, but at the same field and similar powders. They showed they had a DNP spectrum here at the top, which is doesn't show as many features as the one that we see, but it looks pretty similar. And in order to understand the shape of that DNP spectrum, they were able to fit it to solid effect mechanisms from each EPR line. So you see here the blue, the central EPR line has a blue solid effect. The orange also has a solid effect, and the red. And they also included a small positive Overhauser effect coming from the central EPR line. So that suggests to us that we should be thinking about solid effect and Overhauser effect in our sample too. And I can tell you upfront kind of that we also need to be thinking a little bit about the cross effect. And the cross effect here is possible, and I'll show more about this later, but just some important numbers. We're working at 94 gigahertz for the electron, which is about 36 megahertz for the carbon. The width of the two outer EPR lines is about 42 megahertz, so that's basically wide enough to show a cross effect there. And the average dipolar interaction at 120 ppm is about 1 megahertz, so that also seems to match. And I'll discuss more about finding DNP within a single crystallite, but that will come towards the end. So we're going to think about the solid effect and the Overhauser effect and the cross effect. And so here you can see if we're going to think about the mechanisms, we need to decide what we expect the mechanisms to look like in our sample. So if we look at an electron coupled to a nucleus, we can see the solid effect in this type of system if we irradiate on a double quantum or a zero quantum transition, so a transition that involves an electron and the nucleus both changing spin states together, then we can get DNP enhancement. And so if we irradiate at the electron frequency omega E minus omega N, we get positive enhancement. And if we irradiate at omega E plus omega N, we get negative enhancement. So that's what we expect for each EPR line. For the Overhauser effect, we can look at the same spin system, but now if we have cross-relaxation between the electron and the nucleus, so double quantum cross-relaxation or zero quantum cross-relaxation, and if the cross-relaxations are not equal, then when we irradiate on the electron, what we get is enhancement. And so if the double quantum transition cross-relaxation is faster than the zero quantum cross-relaxation, you get negative enhancement. And if the zero quantum cross-relaxation is faster than the double quantum cross-relaxation, you get positive enhancement. And so it's really just a play between the different cross-relaxations, and whichever one wins determines the sign. So now we can go back to our DNP spectrum and try and figure out where we expect each mechanism in the spectrum. So if we look at the central EPR line, the narrow one here, if it gives an Overhauser effect, it seems like here we would expect a negative Overhauser effect, unlike what Lucio Friedman group showed with the positive one. And we can also see that there's probably solid effect here marked in green. We can do the same kind of trick for the two outer EPR lines, and you can see that if there's solid effect, it's just part of a broadening happening on the edges, but that there's a large enhancement here, and it seems like if it's an Overhauser effect, what we have is an Overhauser that's positive on one side of the line and negative on the other side of the line, or what we're seeing is maybe carbon enhancement that somehow depends on the nitrogen spin state. So that's very interesting, and I'll talk about that a little bit more coming up. But I also mentioned the cross effect, and so for the cross effect, in order to see where we expect it, so we need to think about two electrons and a nucleus, and if the two electrons are dipolar coupled and the frequency difference between the two electrons exactly matches the nuclear Larmor frequency, then what we get is when we irradiate on one of the electrons, we get positive enhancement. And when we irradiate on the other electron, we get negative enhancement. And so we expect enhancement separated by omega n. So if we look at the two outer lines, these are the only lines where there's two electrons that could fulfill the cross effect condition. What then we see that it doesn't seem like there's very much of it right here, because we would expect a positive and a negative with a large overlap, and that doesn't seem to match the shape. So really the big question is, what are these big peaks in the DNP spectrum, and what's the mechanism that's coming from them? And so right now I'm going to just say that we'll call them the Overhauser effect, and we'll see a little bit later. But here is a fit of the DNP spectrum using shapes that I calculated for each one of the mechanisms, just by convoluting the EPR line with the expected shape that we think would come from each of the mechanisms. And so you see here at the center there's a negative Overhauser effect, and then on the sides would be solid effect from the narrow line, and also some solid effect from the two outer lines, cross effect, a small amount of cross effect on each outer line, and what we're here calling the Overhauser effect. And so just to do the fit, it was just adjusting the amplitudes of these different shapes in order to get a good fit of the DNP spectrum. So there's a lot of things happening at once, and in order to try and really determine is what we're seeing an Overhauser effect, or is it something else, and how, and can we really tell apart the different mechanisms by other means, not just by the shape of the DNP spectrum? So we did some experiments to check the different experimental parameters that we can change. And so the first thing we checked was the dependence of the enhancement on the microwave power. And almost all the experiments that I showed were at about 200 milliwatt, but we were able to get also one data point at 500 milliwatt with a larger amplifier. So you can see that really at these powers where we're working, we're power limited. The enhancement is expected to go way up if we had more power. And at this range, everything sort of behaves the same, no matter where you look on the DNP spectrum, you're seeing the same type of behavior of the enhancement. And so that doesn't help us separate the different mechanisms too much, but the next thing that we did was look at the relaxation times and the DNP buildup time at different frequencies. And so the T1 here of this sample is has a two exponents, a short time scale and a long time scale. And then when we look at the DNP buildup time as a function of the microwave frequency, we also get something similar. You can see that there's a bit of there is a difference between, there's a difference in the buildup times as a function of the frequencies. So if we look at the short time scale and the long time scale as a function of frequency, you can see that in the center, where we see an Overhauser and a solid effect, the time scales are slightly longer than here on the edges, where we think it's an Overhauser effect, but we're not sure. And also notice that there are some features, small features in the DNP spectrum where the buildup time is very long. So we see only low enhancements at those frequencies, but if we waited longer, we would probably get, the features would be even larger. And so that's interesting to think about for some future work. So really the main point here is that it seems like the timescales on the sides are slightly shorter than the timescales in the center. And that suggests that what we're seeing on the sides of the DNP spectrum are maybe not an Overhauser effect, and maybe something else. So the last thing that we can do is look at frequency modulation. So instead of irradiating directly at one frequency position and then measuring enhancement, which is what we do normally in DNP, you can also irradiate on a range of frequencies. And so here we use a ramp up shape irradiation frequency with a 5 kilohertz frequency modulation, which means that it changes frequency in 5 kilohertz. And the amplitude of the change is about 117 megahertz. So the first thing that we see when we turn on this modulation is that the enhancement goes way up, and now we have more than 100-fold enhancement of carbon at room temperature. And still remember that we don't have high power, so I think we could get even higher. The other more important thing is that you can see that the mechanisms behave differently under the modulation. And so for the solid effect and the Overhauser effect in the center of the line, there's not so much of a change, but there's a quite large change on the edges, and that suggests that the mechanisms are different and that we're not looking at an Overhauser effect here on the side. So back to the big question, which is what is it that we're seeing on these peaks here? And so I'll go back to the Overhauser effect for a second, and I'll tell you that I did some simulations looking at an electron coupled to a nitrogen and a carbon. And here, if we look at the nitrogen, you can see that there are enhancement peaks on the nitrogen at the exact frequency of the two outer EPR lines, and they have opposite signs. So this looks exactly like what we see in carbon. The problem is that when I do the simulation on the carbon, the enhancements don't show up, and there's no way, I haven't figured out a way to have polarization transfer between the nitrogen and the carbon to give us the enhancement here at the correct frequencies without also giving enhancements at other frequencies, which we don't see. And so I couldn't figure out how this actually works. And to me, it suggests that things like cross relaxation, dipolar couplings, which would be the things that transfer the polarization, aren't what's happening here, and that we're not seeing this Overhauser effect. And so the second option of those for those two peaks is the truncated cross effect, which is something that Sunggi Han introduced a few years ago, and they showed a Overhauser effect doppelganger. Basically, they had two types of EPR radicals in their sample, and one radical had very fast relaxation time, and so irradiating on that radical didn't result in enhancement, but irradiating on the other radical did. And let me show it here schematically. If there are two electrons and you're irradiating on the electron here, electron 1, and if electron 1 has very fast relaxation time, you can't irradiate on it and affect it. You can't saturate it, and so you don't get enhancement. But when you irradiate on electron 2, which has a slower relaxation time, you can saturate it and you can get enhancement. So that would look like that's a cross effect that looks like a negative Overhauser effect. And in the other case, if the fast relaxation is on electron 2, then you would get only positive enhancement when you irradiate on electron 1. And so the truncated cross effect seems to match what we're seeing here, because we are seeing positive enhancement on one side and negative enhancement on the other. And if that's really the case, that's what we're seeing, then what we need is another electron pool that has very fast relaxation time that's shifted slightly inward from the actual line that we measured. And that would give us the correct signs. So the question now is, do we expect that kind of EPR line, another pool with fast relaxation? And so what we did was we looked at the probabilities for different dipolar interactions to occur at 100 ppm concentration of P1 centers. And so you can see here that there's a pretty wide distribution of dipolar interactions that are probable. But when we plot the EPR line, when we simulate the EPR line for a single spin in blue or for a combination of pairs, each one with a different probability and a different dipolar interaction, we get the red line. You can see that in the difference, you can see that really the effect is mostly kind of symmetric on the edges of each line. And so it's not 100% clear that there would be a fast relaxing electron group that's shifted inwards to give us the DNP enhancement from the truncated cross effect. But one good thing here is that from these results and from this slide here, where you can see that here what we show is a single crystal of P1 showing the EPR lines as a function of the orientation of the crystal. So at different orientations, there are conditions where within the same crystallite, there are two transitions that can be separated by the nuclear Larmor frequency or close to the Larmor frequency plus the dipolar interaction on the previous slide. And so together, at least we show here that there can be a cross effect within each crystallite. You don't need, and so even if most of this broadening is different crystallites, different orientations, we can still expect a cross effect. And so the last thing that we're doing now, and this is just some preliminary results, is we're looking at single crystals with DNP. And the goal here is to really understand the mechanism that's giving us these large enhancements on the side. And you can see in blue, the single crystal, there's a lot more features happening, even more than in the powder. And so I think that once we are able to really look at the single crystal as a function of orientation and really see what's happening, it'll help us understand what's happening in the powder also. But right now, our guess is that it's a truncated cross effect. So I just want to conclude and say that we show that P1 centers can be sources of large carbon-13 enhancement at room temperature. And what we're seeing is enhancement of about 70 without modulation and even over 100 when we add modulation. And modulation is pretty easy to set up with just an AWG. And so it's not so hard if this is the kind of experiment you want to be doing. These samples show a lot of mechanisms, and we show also that the modulation can affect the mechanisms differently. And that's an interesting thing to think about for future work. And also for future work, we're going to work on the single crystals to better understand the different mechanisms that we're seeing in the powder. And for the future, hope that will help us explain really what we're seeing and how we can use these P1 centers for the next types of studies. So I want to say thank you to Shaker Amanatan at Dartmouth and Kelly and Linta, who helped me with these experiments, and Professor Susumu Takahashi, Zaili Peng at USC, who helped with the EPR, and to Element 6 for the diamond powder. And thank you all for coming to this talk.
All right, thank you very much, Daphna, for your very, very interesting talk. I mean, like, I'm sure that the audience will have a lot of questions, so feel free to put the questions in the Q&A. But before that, I'll just ask you a quick question so that they have the time to put the questions. I mean, it's interesting. And then like, I was about to ask you one question about the single crystal, but you already show it. But this is funny because actually Bob asked me to measure the single crystal of P1 center at low field before, and then I got 3 sharp lines. So looking at here, this is a bit unexpected because like I would expect, you know, nice and sharp high resolution BMP, but it doesn't seem like it. So do you have an EPR spectrum of the single crystal?
No, we didn't measure that yet.
But would you expect like just very sharp 3 lines? And
I think you could expect it to look, it could be 3 lines or it could be up to 5 lines. See, this is a simulation of a single crystal, so there can be 2 or 3 on the side. Depends on the orientation.
Sure.
Yeah.
Yeah. Then you can find one specific orientation why they'll collapse, and then.
Yeah, probably for yeah, that's true.
Yeah. Just curious, do you do all the experiments at room temperature? Was it all room temperature?
Yeah, everything is room temperature.
Can you cool it down to lower temperatures?
Yeah, it could be cooled down, but we haven't tried.
Okay, because like you were suggesting like you would do Overhauser or the cross relaxation mechanisms, and all of this depends on the dynamics, and if we can, you know, if it has a if it does depend on the dynamics, and if it has a change when you cool down temperature, then it will be interesting to see it interplay between all these processes. That
would be interesting, and especially because Lucio showed a positive Overhauser effect in the center, and ours is negative. So, and the main difference between the samples is the temperature. So it would be nice to see that happen.
Okay,
that's something we should try.
Okay, great. So we do have a lot of questions here. So the first, we have 2 questions from Gavin. So I will just read out the first one. What do you mean with clean surfaces? The Rayleigh group have identified the surface dangling bonds as the major electron source, especially for submicron diamonds.
Okay, so I think I was talking about in silicon particles. There's a ton of if the particle is silicon, then usually there's an oxide on the surface, and then there's a lot of surface defects in the interface between the 2 layers. And I think that might be something that you wouldn't expect that for diamonds, but maybe very small. It's true that at very small sizes there would be more. Yeah.
Okay, here's the second question. How do you interpret the 2 components in the build-up, the fast and slow? A spin diffusion step like in silicon particles might be unlikely due to the homogeneous distribution of the P1 centers and their high concentrations. Yeah,
that's true. I think that I still would I still think about it as kind of spectral spin diffusion of the polarization, because there's still carbons that are close by to the electrons and some that are farther away that need to be enhanced, even though we're talking about natural abundance. So the carbon concentration is pretty low, but still.
Okay, Amrit said, nice talk, Daphna. What kind of motions do you think could cause the Oberhauser effect?
Yeah, so that's another question, because we were thinking about Zener-Landau effect of the jumping of the nitrogen, but according to what we've read in the literature, it seems like sorry, not the Z, that's not the right name. Let me find the slide, sorry. But sorry, I forgot the name, but we expect this mechanism to be kind of slow and about 1 hertz, and that would be too slow in order to cause an Oberhauser effect. And so it's not clear to me really what would be the effect here, but we're still thinking about it.
Were you looking for the word Landau-Zener? Or okay, never mind. I'll
find the slide. I'm sorry, it
okay,
just
no
like escaped my head right now.
Okay. So Beyond has a question. Cross effect should show significant increases if you do magic angle spinning. Do you have any plans in doing that?
Magic angle spinning, no. Well, I mean, we could take it to some other magnet, but not right now, I think.
Okay. Next question from Aaron. Can you comment on the relative amount of NV and P1 centers in your diamond samples? Can this ratio be controlled using synthesis or during synthesis?
I think the P1 is usually about 10 to 100 times higher in concentration than the NV centers, but I'm not 100% sure on that. And I'm also pretty sure that it's possible to control them, but here we just got a sample from the company, and we just used it without controlling anything or asking for anything too special.
Yeah. Okay, Jeff says, nice talk, Daphna. And he asked you if you have recorded DNP as a function of temperature. I mean, it's basically the similar question that I asked previously. And then this is something that you plan to do in the future, right?
Mm-hmm.
Yeah. Okay. Next question from anonymous attendee. Any possibility that the center DNP peak could be different from Oberhauser?
I mean, it's possible, but I don't know what else it would be. And yeah, I hadn't thought about that, but I don't know what other mechanism would look like that and be found at the center like that.
Yeah. So you mentioned a solid effect, cross effect, Oberhauser, and do you see any possibility of having something like thermal mixing if you use? I don't know.
I think for thermal mixing, what we would need is a homogeneously broadened DPR line, and the line should be broader than the nuclear Larmor frequency. So I'm not sure that the center line fits that. I think it's too narrow for that, but
okay. Yeah. All right. Next question from Gavin again. What are the T1E times at the field that you do? 3.
So we haven't measured them actually in this case, but we did measure T2. No, we did. No, sorry, that was the T2. Yeah.
So how do you do the EPR? Was it just a CW field modulation, or was it with a pulse EPR? Or can you comment?
Yeah, it was pulse EPR at 230 gigahertz. So but we don't have any. We didn't do anything at W band at 94 gigahertz.
Okay. Pulse EPR at 230 gigahertz. Okay.
Yeah.
All right. Fred say, nice work, Daphna. Yeah, exactly. Yeah. Electron T1T, T1T2. Maybe doing something at low temperature might help you discuss. Yeah, exactly. We have discussed this before. Okay. Last question from anonymous attendee: is uniform distribution of electrons a good assumption?
I think so, because we didn't try and synthesize anything, and so I think that it probably would be a uniform distribution or close to that. The particles are large enough that the surface defects are not so visible, and mostly what we're seeing is the P1 centers.
And then like the P1 concentration that you use here, I think it was 110, 130 ppm. Is this something that comes naturally? Can you ask like element 6 to provide you diamond with a different P1 center concentration?
Yeah, I think that they have a way of controlling it, or at least telling apart and finding different, depending on how they create the diamonds, they can get different concentration.
And would
I want to make a correction about the thermal mixing, because I don't think you don't need to be broader than the central line, but it does need to be homogeneously broadened. So I'm not sure that I expect that here, especially at room temperature, but maybe at low temperature.
Yeah, I was just thinking like if you can get different concentration from element 6, then you can probe Olhauser, solid effect, and all different mechanisms. Because
that would be
effect.
really interesting at to go to very low concentrations and see what we see.
Exactly. Yeah.
Well, you can also do a field dependence where the solid effect should go down as omega naught squared. Supposedly the thermal cross effect should go down as omega naught, and then the Overhauser effect, in the 2 or 3 cases we've looked at, maybe 2 cases we've looked at, should go up as you go up in magnetic field. So a field dependence of that line shape of that field profile, microwave field profile you have, or Zeeman field profile you have here, would really could give you a lot of information about the Beckett. I mean, you've got a lot of things going on, which is really very interesting, very nice. Yeah, beautiful, a beautiful example of a crazy Overhauser, a crazy DNP system anyway. Yeah.
Yeah. No, you're right. I think that it would be smart to go to different fields.
Well, I mean, so you could look at 140, 250, you could go all the way up to 900 megahertz, 593 gigahertz or so, and see what how all these things. And you can do magic angle spinning with this too. So
that's what I was going to say. If we're going up, we can also do the magic angle spinning.
No,
you can do everything in your lab, Bob.
Daphna could come spend a sabbatical and we could look at the diamonds.
Exactly. Yeah, you have all DNP at different fields, different capabilities.
That would be nice. Yeah.
Okay. All right. Well, let's go on to the second speaker. So we're very fortunate today to have a second speaker of Christophe Copéret, who is a very, very well-known member of our community. He was an undergraduate in Lyon. He did his PhD in the United States at Purdue University, and then was a postdoc with a very famous organic chemist who was at MIT for quite a while, Barry Sharpless. And then he moved back to Lyon, where he was a CNRS research director. And then finally, a few years ago, he moved from Lyon over to Zurich at the ETH, where he's now a professor in I think inorganic or organic chemistry. I don't remember which. Inorganic chemistry. Okay. And today he's going to tell us about NMR chemical shifts beyond numbers and signatures. And you've got the wrong. You're muted. You're muted. And you have the wrong screen. You need to unmute.
Okay, now I'm on mute, and now I have to put the right screen. That's always the same problem. I changed at the last minute my setting. Okay, so let me put my presentation on. Thank you very much, Bob, for a kind introduction. I'm happy to be part of this wonderful community. Is it the right screen or not? If not, I change.
That's not the right. No.
Okay, it's coming to be the right one.
There you go.
See, there's some hope. Okay, well, thank you very much, Bob, for a very kind introduction. Again, very happy to be here today, and I will try to keep quick. So I don't see my screen anymore. That's a problem. You see, I have plenty of new screen that appeared. Sorry about that. This is actually kind of funny. I have many screens that appear that was not there before. So sorry about that. This is kind of embarrassing. Okay, so let me share the screen. This should be the right screen again.
No, oh, that's
No?
good. That's good. That's good.
Exactly. Okay. Well, now I can start. So again, thank you very much, and I want to share with you what we have been doing in the past 5 years. So maybe before that, just to remind that we have two major activity in our group. One activity which has been something which is very close to Bob Griffin is doing, and we actually basically in a way was inspired by his work when I work heavily with Lyndon Hensley, was trying to enhance obviously the signal of surface species, something that we call basically surface NMR spectroscopy. And obviously, if you start to have a lot of signal, and you can start to imagine many new experiments. And let us basically in what we really love to do nowadays is try to understand the origin of NMR chemical shift. And what I want to share with you today is our passion for these values and these numbers, and trying to see if we can actually make sense of these numbers and hopefully create new chemistry from this number. And this is actually a work that has that we started actually with a bunch of friends, Audrey Eisenstein from Shimon and Dick Anderson from UC Berkeley, and a series of students. In particular, I would like to highlight the work of Christopher Gordon, and then you will see some related work of Christian Henger, Lucas Leitch, and Ilya Morose. And I want to try to share in 20-something minutes what we have been doing in this area of NMR chemical shift. So why somehow we were drawn into that? And again, as Bob Griffin said, I have a past in organometallic chemistry and organic chemistry as well. And what's always intriguing to me is if you look at carbon-13 chemical shift for organic compound, you can easily distinguish alkanes from alkyne and alkenes, but at the end of the day, they span a rather small bandwidth of chemical shift if we compare to organometallic compound, where alkylidines, which correspond to this alkyne compound around 300 ppm, carbenes and alkylidines, which are also very close from MIT with Professor Schrock, also a very good friend of mine, where you see that they span a very broad range of chemical shift, basically across 150 ppm, and then metal alkyl, so carbon directly bound to metal, can actually have very broad range of chemical shift. And when they are cationic species, they start to have actually very large chemical shift value, which are actually very close to become the one of basically carbon sp2 bound to carbon. And this is actually a way to illustrate these numbers here. So you can see that you have a very broad range of chemical shift, and they seem to vary as a function of how many bonds you have with a metal center. And obviously, this is due to the fact that these carbon have very large anisotropy. And again, if I compare for very simple CSP3 carbon, an alkane versus a metallo-organic compound, you can see that if I move across that series, you can see that actually suddenly you can actually have very large span, very large anisotropy when I look at metal-carbon bond. And the same is true with metal alkylidine versus the corresponding alkene species, where you see that you have actually much broader chemistry anisotropy, and with very de-shielded basically value for delta 1,1. I'm going to introduce all these terms very soon. Okay, so when we see that the breadth of chemical shift and this breadth of basically chemical shift anisotropy, obviously this immediately come to mind that maybe we want to understand a bit better what is the origin of this chemical shift anisotropy. And this was studied a lot in the 1970s and 80s for organic compound, but it has been a bit less studied for organometallic compound, in particular in connection with reactivity. But before I go into that, to make sure that we are all on the same page, I will come back a couple of steps backward and try to look at what is a chemical shift, because obviously some of you may not be aware of subtleties of chemical shift, even though this is undergraduate chemistry. So typically a chemical shift, as we know, is a tensorial value. And typically it's if you look in solution, you have typically very sharp line. And the origin of the sharp line is because basically you average the three principal components chemical shift tensor. And in fact, if you would actually take ethylene, we very well know that there should be one single line at 130 ppm. If you would actually do a powder spectra of ethylene, you will see this very broad line, and this very broad line and the extreme value of this broad line correspond to a specific orientation of ethylene with respect to the B0 field, and the most deshielded value, delta 11, would correspond to ethylene being oriented basically perpendicular to this B0 field in a sense of this carbon-carbon bond and the pi frame. Okay, and obviously, when you see that there's a lot of information about the electronic structure of this compound. And obviously, what we want to do is to actually go deeper in trying to understand these values. So typically, we measure chemical shift in the lab, and chemical shift is related to a chemical shielding, which is an intrinsic value property of basically a nuclei. And typically, if we look at what this chemical shielding is, it can actually be separated into two main parts, what we call a diametic component, which is often very constant across one specific nuclei and a broad range of molecules, and it corresponds to the shielding of the nuclei by the core electrons, if I want to simplify. While there is another term, sigma para, which corresponds to basically the shielding of the nuclei by the valence electron. And this explains why chemical shift windows are very large for basically carbon 13 and nitrogen 15 and all the other elements of the periodic table, but basically proton, which has actually a much narrower chemical shift window. And the reason for this large chemical shift window, this sigma para, is can be related to an extraction of the Ramsey equation, where basically you can see that this sigma para is related to basically a relation between, or a coupling between occupied and empty orbital by the operation of the angular momentum. And this value is particularly large, is the difference of energy between occupied and vacant orbital are actually close in energy. And this is actually a very good news for a chemist like me, because it means that we are addressing the frontier molecular orbital and not, which has to be related to reactivity. So again, to dwell a bit further on that, if I look at this operator in a very simplified way, if I apply my operator along the z-axis, I will basically rotate this orbital by 90 degrees in the case of a p orbital, which means that the LX operator is actually very similar to a rotational operator. And because of that, basically, it explains why ethylene has actually a very deshielded chemical shift compared to an alkane, is because there is actually a closed field orbital, close in energy, which is related by basically this rotational operator to the pi star orbital. And because of that, this leads to a very good, strong deshielding of the alkene moiety. So now let's dive and go into trying to understand what is the origin of this very large chemical shift in chemical shift anisotropy in this metal carbon double bond. And I chose this example today again in the honor of my very good friend Dick Schrock, which is also a very good colleague and friend of Bob Griffin. So the way we are going to do that in our laboratory, and I'm not going to go into the detail thereafter, is that we are going to measure basically the chemical shift, basically the powder spectra at actually a low spinning rate to be able to extract the principal component of the chemical shift tensor. We are going in a second step to actually calculate this chemical shift tensor by DFT calculation at very high level. And this will actually allow us to actually orient the chemical shift tensor with respect to the molecular frame. In particular, we want to know what will be the direction of delta 11 component with respect to this molecular frame. And then based on actually natural chemical shift analysis, we are going to transcribe what is giving rise to this very large chemical shift value to specific, basically, molecular orbitals. This is actually going to be the methodology that I'm going to use throughout my presentation today. And from that, we'll be able to relate a chemical shift value to basically specific frontier molecular orbital and their contribution to the chemical shift. So if I come back to alkylidine, I told you that they have a very, very large chemical shift value, above 200 ppm, if I compare to ethylene, which is around 128 ppm, depending on obviously on the solvent. And in what we can see is that, here I've shown you something that has been developed in a group of Professor Schrock at MIT, and then this one in the group of Professor Grubbs at Caltech. And we can compare to the infamous Fischer carbene. And if you look at this series, and I'm not going to go into too much details, again, as I said, we had very, very large chemical shift value, which are very similar to a carbocation, which is kind of interesting. And typically, Fischer carbenes are typically larger chemical shift value. So this is called Fischer carbene here, has actually made a large chemical shift value than a classical alkylidene developed by Professor Schrock. And what actually is very interesting for us is that if you look at the chemical shift as a function of the metal, chromium compound actually have larger chemical shift than molybdenum and ruthenium, which are larger chemical shift than rhenium and texane. So it seems like there is a relation between being 3D, 4D, and 5D metal and chemical shift. So this is actually, as an organic chemist, as I was trained, is actually kind of interesting to see this type of trend. And what we want to do now is try to understand what is the origin of that chemical shift. So clearly, if you actually measure and calculate the chemical shift of these various compounds, what we can see is that this isotropic chemical shift is mainly, this large value of chemical shift is mainly driven by the large value of delta 1,1. And so basically delta 1,1 is driving this chemical shift. And the question obviously is, what is the reaction of delta 1,1 in this type of molecule? And this is actually true for alkylidene, but also for this Fischer carbene. And I'm not going to go into the details today because it's not a lection of organometallic chemistry, but it's about a discussion about what we can do with this value to understand basically chemical reactivity. So as I said, delta 1,1 component is actually in all the compounds I've shown you so far, this alkylidene compound, they are always oriented perpendicular to the metal carbon bond and perpendicular to the pi frame of this metal carbon bond. So this is actually very interesting to see that it's actually very, very similar to what I've shown you with ethylene molecule. But what you can do then is what I told you, you can actually now try to understand what molecular orbitals actually correspond to this, relate to this very large chemical shift value. And you can see that across all these compounds, you can see that, as I told you earlier, the sigma dia, so the diamagnetic component of the chemical shift tensor, is basically constant across this series. And what varies most is this paramagnetic component. And actually, if you look closely, you can see that you have always the same pattern for these alkylidenes. While if you look at this, what we call Fischer carbene, the pattern is quite different. So there is some kind of fingerprint of electronic structure of this compound as a function of basically the metal site. But more importantly, if you look more closely at this Schrock alkylidene, you can see that the dominating factor that lead to a very large chemical shift value is due to the metal carbon bond. And in second term, actually, the pi bond of the metal carbon. And we can try to understand why is this metal carbon bond so important in driving the chemical shift in this compound. And in fact, by purely symmetry, since you know that this chemical shift component is perpendicular to the MC frame, and that the metal carbon bond is a driver of the chemical shift, actually what you can actually identify is that there must be a low-lying pi star orbital close in energy to the sigma bond to drive basically this chemical shift. That's actually what this analysis can do. And you can see that similarly, you can see that the pi also contribute, because if you actually do a rotational operation of this pi star, you can actually build this sigma star. And we know that basically this also should be close in energy, even though they should be further away than these two orbitals. So now that we understand the chemical shift value, we can actually do the same thing with all principal components, but today I will actually only focus on the most important contribution of this chemical shift value. And so basically what we can actually now, you can actually derive what you have learned from NMR to actually build up a very simple molecular orbital diagram, a typical basically Rudolph-Mann chemistry. And actually what I'm telling you so far is that basically the chemical shift is due to a small difference in energy between the sigma bond and this pi star orbital. This is actually what is actually driving the chemical shift energy. Based on that now, and I'm not going to go into the details today, you can understand a lot of reactivity of this alkylidene. In particular, you can understand why there was this relation between 3D, 4D, and 5D metal, because as you go down into a column, you actually increase the energy difference between bonding and anti-bonding orbitals. That's what we teach in basically second year inorganic chemistry. And as you increase this difference of energy, you will actually decrease the contribution of the coupling and thereby decrease the chemical shift. So you can see that by using NMR spectroscopy, we can actually reconstitute basically what would be a molecular orbital diagram of a molecule that we can derive, that we can actually make in the laboratory. So, again, because at MIT, I have to discuss a bit about the work that we do a lot in collaboration with Professor Schrock. And again, if you do at olefin metathesis, one of the key reaction intermediates is metacyclobutane. And there's a lot of question in the literature when we started that work about, why a structure which has this trigonal bipyramid structure is actually on the reaction path, and why this metacyclobutane, which has a square pyramidal geometry, does not contribute to the reaction in olefin metathesis. And more importantly, what we noticed with my colleagues, Odi Eisenstein and Dick Anderson, is that all the metacyclobutane that participate in that reaction have a very specific type of chemical shift. So alpha carbon is highly deshielded at around 100 ppm, and the beta carbon is very shielded. Well, all metacyclobutane that do not contribute to this reaction have actually rather shielded or similar chemical shift, whether you have the alpha and beta carbon. So it seems that NMR can distinguish, very simple solution NMR can distinguish of what can be a catalyst and what cannot be a catalyst. And based on that, what we did, we actually measured, calculated this chemical shift tensor, and we can actually see that the chemical shift, the principal component of the chemical tensor, the most deshielded component, delta 1,1, is oriented again perpendicular to the ring of the metacyclobutane in the case of the active metacycle. And based on calculation, we can actually trace back again to this metal carbon sigma bond, which means that there must be a low-lying empty orbital to be able to couple with that metal sigma bond to explain this very large deshielding value. And in fact, if you look very carefully at this molecular orbital representation of a metal carbon bond in a metacyclobutane that is active in metathesis, they are very much related to the corresponding metal carbon bonding orbital that you would actually imply in a corresponding alkylidine, which have to react with olefin to make this metacyclobutane. And basically, what this scheme is trying to tell you is that basically all the metacyclobutane that actually carry out metathesis, whether they are directly with titanium, molybdenum, tungsten, or ruthenium, which are very different classes of catalysts, actually obey by the same rule of symmetry. You need to have an empty orbital, empty that point into the ring. And when you have an empty orbital that point into the ring, you can actually allow to make this pi interaction, which actually connect these to the chemical shift value, and you can actually predict what metacyclobutane can be active in metathesis. So just one more slide on this topic to show you that what we have seen with this metal alkylidine, this metal carbon double bond, we can actually apply the same reasoning for the metal alkyl. But obviously, when you discuss about alkane in organic chemistry, you should expect a sp3 carbon and a very isotropic, basically a chemical shift anisotropy. And in fact, what you can see is that actually this is actually true for most compound. But when you start to have this cationic metal carbon bond, you have to have another anisotropy which is actually very close to what you actually see in an alkylidine. And what actually is very interesting as an organometallic chemist is that these compounds are very well known to be a highly efficient olefin polymerization catalyst, while all these compounds are actually not able to do olefin polymerization. So obviously the question I can ask is there a relation between this anisotropy and the reactivity of these compounds? Again, to make a long story short, we did all the analysis and we could actually show that the reason of this anisotropy, as found by NMR spectroscopy, is that delta 1,1 is actually oriented perpendicular to the metal carbon bond and is connected to the fact that there must be a very small energy difference between a sigma bond and a pi bond. And you don't actually expect to have a pi bond between a metal carbon, basically sp3, but it tells you that actually a metal which has a low-lying empty orbital of the right symmetry is able to actually interact with a p orbital on carbon in such a way that it create this anisotropy and also very likely the reactivity, which means that basically while we write typically a metal carbon bond and a sickle bond, NMR spectroscopy tells you that actually the better way to write this atom, this molecule, is actually that there must be a partial pi character in this metal carbon bond that explain the NMR property, but very likely also can explain the chemical reactivity of this compound. Because as I told you, a compound that has this very large anisotropy is typically connected to chemical reactivity, in this case, olefin polymerization. So basically, typically, when you used to teach organometallic chemistry before our work, you will always discriminate two types of mechanism, and people will always say that olefin polymerization has to take place via this mechanism and not via this one that implies the formation of a metal alkylidine. What we have shown in our work using NMR spectroscopy is that actually the truth is in between the two mechanisms that were proposed for basically 30 years, and that you actually need this pi bond character to enable basically a chemical reactivity and olefin polymerization. So actually now NMR become a very, very important descriptor of reactivity. And when I gave these talks typically in companies, the people are the most interested in these talks are typically the patent lawyers, because now having a chemical reactivity descriptors, you can actually start to embrace basically chemical formula and a way to actually describe reactivity in patent literature. So we have applied that to many systems, and we have created a lot of passport of molecule because every basically molecule has a very specific fingerprint of this chemical shift anisotropy, and we can actually now predict chemical reactivity across a broad range of catalysts. And to finish my talk today, I would like to explore other areas, which is not only organometallic chemistry, but areas of basically surface chemistry. So a typical example that we do, that we teach in basically surface chemistry is that if you look at the field of heterogeneous catalysis, a lot of people use probe molecule like pyridine to try to understand basically the acidity of surfaces. And one can easily distinguish when you add adsorbed pyridine on the surface, you see that you see a very complex spectra, and all these lines correspond to specific pyridine interacting with the surface of an oxide material. And you can see that while free pyridine is expected at this chemical shift, you see there is actually a strong shielding of this pyridine upon adsorption of a molecule. And what we know is that this one corresponds to a pyridine that has abstracted a proton at the surface, so it's a pyridinium, while all these other peaks correspond to basically pyridine which are interacting strongly with surface sites. And it, again, by doing the same approach as what I've shown you earlier on organometallic compound, we can basically show that the origin of this now shielding is due to the fact that when you interact pyridine with either an atom, an H atom, which is a weak, basically a branchette acid, H bonding with nitrogen or Lewis acid, you actually quench basically the delta 1,1 because you interact Lewis acid with this lone pair, which is the origin of this very high chemical shift value for pyridine. So if you make a bond between pyridine and Lewis acid or H bond, you will actually quench this lone pair, and by quenching the lone pair, you will actually decrease this chemical shift. And it turned out that actually the chemical shift is directly related to the difference of energy between this new bond and basically empty orbital of the pi star on the aromatic ring. And actually, there is a direct relation between the chemical shift and basically the adsorption energy of that molecule on the surface, basically. So you can actually relate thermodynamic basically enthalpy with basically chemical shift. So again, chemical shift again is a very, very important tool to actually understand not only chemical reactivity, but basically surface species and relate to acidity. Let me finish with one last example. It's something that actually come back to my postdoc years when I was with Professor Sharpless. And what I noticed when I was working with Professor Sharpless is that if I look at metal peroxide, there are two types of metal peroxide. You have H2O2 and TBHP, which are peroxide which do not allow to oxidize olefin, what we call epoxidation. And there are peroxide like MCPBA and DMDO, this molecule with a cyclic structure, which allow to do epoxidation. And if you look very closely, what it looks like is that the one that do not allow to do epoxidation have a chemical shift around 200 ppm, while the one that do epoxidation have chemical shift around 300 ppm. And it turned out that this seemed to be related to delta 1,1 component. Okay, so again, delta 1 component is driving the chemical shift, and it seemed that there must be some information hidden in this NMR chemical shift that explains the difference of reactivity between these two types of peroxide. again, to make a very long story short, what we have shown is that this origin of difference of chemical shift is due to the difference of energy between the high-lying pi star and a low-lying sigma star molecular orbital of this peroxo species. And when you have a cyclic structure, like in MCPBA or DMDO, you have a perfect system to actually have a fully coplanar lone pair on oxygen, which actually raises the field pi star, decreasing this energy and driving the chemical shift, but also the chemical reactivity, because at the end of the day, the epoxidation is nothing else but a transfer of an electron from the pi orbital to the sigma star and a back transfer of this high-lying pi star orbital full of electron into the upper orbital of the basically pi star of the olefin. And so what we have shown in, again, this NMR study is that we can actually, again, relate chemical shift to chemical reactivity and show that basically a peroxide is nothing much different than what we actually observe also in transition metal catalysis. Just to close, is that we actually then have used this to actually understand the active site structure of a very, very important catalyst in industry, which is TS1, which enables the epoxidation of propylene into propylene oxide. This process is one of the greenest processes you can imagine because the only byproduct is H2O, is water. And the big question in that field has been, what is the structure of the active site? And what has been proposed for many years is that the structure of the active site is actually an isolated titanium atom that actually activate H2O2. And to make a long story short, because I think I'm running out of time, and I don't want, I think it's important to keep time for some question. What we have shown is that through that study is that while people were actually proposing that the active site was an isolated titanium site, we could actually show through a very complex and detailed NMR analysis that the active site is a dinuclear site, which allowed to activate H2O2 to make actually a peroxide. And this was actually possible thanks to our understanding of NMR spectroscopy, and in particular, NMR chemical shift parameter. So to conclude, what I hope I have convinced you is that NMR chemical shift is a very powerful descriptor. It's a very powerful descriptor because it actually is directly related to frontier molecular orbital. And it's a unique operator for spectroscopy because in contrast to what you see in X-ray absorption spectroscopy, IR and UVVs, this operator actually is related to a rotational operator. And being related to a rotational operator, it allows you to probe orthogonal orbital, which means you relate sigma and pi symmetry. And I believe this is one of the most important concepts in chemical reactivity, that when sigma and pi are talking to each other, you actually open new pathway of reactivity. And now we are exploring further this field, moving away from ligand NMR to metal NMR, and we are exploring that with many people that you know around the table. So as I have shown you, I hope I have convinced you how important chemical shift is, and I'd be more than happy to answer your question. And as I said, most of the work was done by Christopher Gordon and some of the people that you have seen highlighted in red in this talk. With that, I would be happy to answer a question. I'm happy to thank you very much for your attention and for inviting me today.
Okay, thank you, Christophe. Okay, for a really nice talk. I mean, we've been measuring shift anisotropies for years, solid state NMR, but I can't say that anybody has done the sort of careful analysis that you've worked through here, especially for the metals, which are very big. The shift anisotropies are really quite big. Okay, so let's see. In the chat, is there a question in the chat? Okay. So wait a minute. All right. There's one in the Q&A already here. Let's look at that. Okay, so Fred asks, in the titanium olefin polymerization catalyst that you showed, had a partial pi bond character. Do you see a large distortion of one of the titanium carbon proton bond angles by crystallography? And then
very good question, Fred. Maybe we can go to the next question after. So we cannot measure crystallography on this system, but if you look at the calculation, the titanium carbon H, the angle is 90 degrees. So, in contrast to a typical sp3 carbon, where you would expect basically something close to 109, we actually have a very, very acute metal carbon H bond angle, which people refer to as alpha agnostic interaction. And to us, it's actually a way to show that you have this pi bond which is being built inside this metal complex. And this is due to this presence of this low-lying empty d orbital, which has the right symmetry to interact with the p orbital on carbon.
Mm-hmm. Okay, he says related to this is how large is the barrier for the titanium carbon rotation, and is there a rapid exchange into the pi bond by pi bonded atom? Okay.
I think people have tried to measure that in solution, and no one has ever seen any barrier. What people have seen is actually a very low JCH coupling constant. So JCH coupling constant can go down to 90 Hertz, which tell you that you have a very much elongation of the CH bond. But so far, as far as I know, no one has been able to identify a barrier for this system, which is not true in the case of beta H agnostic. You actually see some barrier of rotation.
Okay, so have you, I mean, you've been looking mostly at carbon shifts. I mean, so we did some work with Schrock and Kit Cummings quite a while ago now.
On phosphorus, yes.
Yes, and you know, we saw like in the metal carbon, metal phosphorus triple bond.
That's correct.
It's like a 2300 ppm shift. It was really. Have you looked at that class of compounds?
So my colleague Odi Eisenstein has done a bit of phosphine, but in the case of phosphine, because they are sp3, the chemical shift is not so sensitive. However, in contrast to what you have shown with Kit Cummings, where you had this 2000 ppm, is because they are sp hybridized, so they are specific case. So we have not looked so much at phosphorus, much more N15. And so what I really like is like pyridine, because pyridine is a pi system, there's actually a very strong coupling between the sigma, the lone pair, and the pi star. So anything which is sp2 is very, very sensitive to anisotropy, similar to sp3 to sp, but sp3 is less sensitive to anisotropy. So now what we are moving on, and we work a lot with Aaron Rossini and Lesage, is more on the platinum NMR. Some work related to what Auchbar has done a while back, is to look at anisotropy in metal, where here chemical shift anisotropy can be 5,000, 6,000 ppm. So I think there's a lot of things to do in metal NMR in that respect, and I know many people are looking at that.
One of the things that that you've seen that's somewhat different than what we've seen initially by shift anisotropies is that, so for example, it used to be that in at least carbon compounds, carbonyls, the sigma 1,1 and 3,3 elements would stay put. And that what you would see would be a movement of sigma 2,2. Now you're seeing sigma 1,1 really going up and down really quite a lot. So have you looked at, I mean, what's involved when you have sigma 2,2 only moving to shift around, you know? I mean,
so you know, typically in the case of metal complex, maybe I should put my presentation back on. I will try to look if I see my, typically we see that in most metal complex, it's actually sigma 1,1. But in one specific case, and I think I have to put, do you see my screen again? Yes.
Yeah.
So in one specific case, and I hope I have to find it, but I will not have the data here. But in the case of the ruthenium catalyst here, that you see from the Grubbs complex, and what is happening is that actually both 1,1 and 2,2 are moving. And it gives actually, it depends actually on what is a component here. So as I told you earlier in that slide, it actually depends very much on who is contributing to sigma 2,2. Okay, and so if you look at this orbital here, sigma 2,2 is driven mainly by this connection between the pi, field pi, and basically another sigma of the CH. So when you see that, that means that you have a very different electronic structure, which is related to making something which is more sp2. That means when the metal has a lot of electron, it gives back to the metal center. And then you start to make a bit what we call hyperconjugation, and then you see that appearing. So this is it's a case-to-case basis, but I would say in most instances, what we have found is 1,1 is driving, and in few cases you see that 2,2 is driving, and in few cases what is happening also in this system is that 1,1 and 2,2 can invert.
Yeah.
And this happened, for example, in what I didn't discuss, I think if you take the infamous Schrock compound, you see, the one that gave him his Nobel Prize here, it turned out if you look at the tensor of this compound, it's actually closer to be SP than to be sp2. Because you see the 2 has moved from basically here, so below the chemical shift, to above below the isotropic chemical shift to above.
Yeah, yeah. Mm-hmm.
So when you change hybridization from sp2 to sp, you see delta 2 contributing. But when you only see a contribution of more on the pi system, it's actually delta 1 which is moving.
Yeah.
So it's really about, again, symmetry of which orbital actually contribute to the chemical shift.
Yeah. Mm-hmm. And we've seen similar effects to this. I have to think. In retinal nitrogen shifts. And these are carbon that you're talking about here, but the retinal shifts. Again, you see, well, in that case, it's the which element is it? It moves way downfield when you protonate. That's maybe what's happening in the pyridine case.
Exactly. So in the case of pyridine,
yeah.
So if I come back, maybe I was a bit fast because I was late. In the case of pyridine, it's exactly what you say. It's actually reversed. If you have pyridine, you actually go shielding.
Yeah.
And the most shielded one is when you protonate. So this is a protonate form of pyridinium. And you see it's off the scale. See, if you look at that, it's off the scale. So any Lewis acid, Lewis base interaction is actually linear as a function of delta H of adsorption with chemical shift. Well, when you protonate, because now you make a conjugated base, and therefore the energy of adsorption is unrelated to the interaction of this newly sigma bond, then you're actually off the scale and you actually have very shielded chemical shift. And the reason for that is basically in that case, in contrast to the metal where you combine a sigma with a low-lying pi star, here you actually quench the lone pair, which is important for the coupling with a pi star. So this is just the origin is different, basically.
Oh, yeah. Mm-hmm. There's another question from Amrit. It's what other chemical insight could metal NMR of organometallic compounds provide regarding reactivity that you don't already learn from the C13 CSA? Okay. So
very, very good question, Amrit. So in some cases, you learn the same thing, but recently we are writing currently a paper where in carbon NMR, because the chemical shift window is still rather small, even in alkylidine, the chemical shift window is 2000. Recently, right now, we are writing a paper on molybdenum NMR. And in that case, the chemical shift window is 3000 ppm. So then you can actually pick up subtleties that do not appear in the carbon 13 NMR. So I think it's complementary. It's a bit like, at the end of the day, if you look at a catalyst, you have a metal, a metal catalyst, you have a metal and the ligand. Ligand inform you about the electronic structure of the metal, but also as a metal inform you about what it's doing to the ligand. And we should never forget that the ligand is often what is actually being part of the reaction, as in olefin metathesis. And in some cases, the ligand is only modifying the electronic structure of the metal. So it don't depend what you are looking at, basically. So I think for me, they are complementary. And it's a case-to-case basis again.
Okay. Okay, Kong, do you have any additional?
Yeah, well, actually, in the attendees, we have someone raise his hand or her hand. Yao, would you like to ask your question?
Yeah. Yeah, there's a question.
Yeah, you want to unmute yourself?
Yeah. Sorry, I just did a mistake, but I would like to ask for the paramagnetic metals, and we have paramagnetic metals, and how can we get CSA of the paramagnetic metals? Did you have tried that?
So we have worked a lot with Guido Pintaguda. So typically, when you have a paramagnetic metal, that gets a bit more complicated because you have to be able to record the spectrum of the ligand. And so in favorable cases, so if you do copper 2, or we have done titanium 3 with Guido and other systems, you may be able to look at the anisotropy of the ligand. So the problem is that in that case, your interpretation is complicated because now not only you have a chemical shift entropy arising from basically the FMOs, but also of the interaction of the electron with the adjacent nuclei. So you have a pseudo contact shift and contact shift, and the information is there, but it's far more complicated. So in that case, actually, what you can actually do EPR, because with EPR, you can actually do the same analysis that I've just explained. So by EPR spectroscopy, you're also coupling FMOs with the electron. So if you actually measure a tensor by EPR, you will actually get the same information as NMR as I showed you today. So again, DPR, we know very well that when you have a parametric element, the question is that can you do EPR or can you do NMR? In some cases, it's not always possible to do the two. But you can actually do the same analysis. But I would say the analysis for the NMR of parametric material is actually a bit more convolved, because you have not only the anisotropy coming from the effect of the electron on the nuclei, but also the pseudo contact shift and the contact shift. So that makes it a bit more complicated. And I think calculations are not yet at the level where you can actually trust. And actually, I don't think actually it's possible yet to actually analyze NMR as we can do by this chemical shift, natural chemical shift analysis.
I see.
But I'm sure people are working on it. Like people like Frank Nese, Auschbar are heavily working on trying to, can you extract molecular orbital interaction information from a chemical shift or pseudo contact shift or contact shift.
Okay, I see. And also, I think you have like DNP 600 and DNP at your lab. So you also do like this experiment, the CSA experiment at the DNP machine or?
Exactly. So for example, in the case of pyridine that I've shown you now, this was all done by DNP. So I didn't discuss about DNP, but a lot of things that we are able to do are enabled by DNP sense. So because this spectra can be recorded in a few minutes, and then what we can do is we can actually do either CP mat or pass pieta, and then you can actually extract by 2D NMR the anisotropy. Because at the end, what I didn't say maybe very well today is that we always try to benchmark our calculation by measuring anisotropy. We cannot only trust calculation, because often when you do calculation, you have compensation error where the isotropic chemical shift is calculated properly, but the anisotropy is wrong. And to be able to do that analysis, you need to actually make sure that the principal component that you calculate actually match the experiment. And only then you can do this analysis. So
I see.
Yes, to answer your question, again, we definitely need DNP for a lot of this measurement, because we can actually extract basically a CSA by 2D NMR. And this is actually also with label. So it's labeled pyridine on the surface with DNP.
I see. Because DNP like usually do 100K, because you do like here is seem to statics experiments because you mentioned
this is 100K as well, because in the case of pyridine, pyridine hops from side to side. So if you do that at room temperature, you get an average. You have a chemical exchange, and actually the information you get has no information. So you actually work in a frozen state anyway, and you use DNP to enhance your signal.
I see. Okay. Yeah, thank you.
And also, it's also important to do low temperature, because again, if you want to measure CSA, we should never overlook dynamics, because if you have dynamics, you can actually average your CSA. So again, because we want to measure the CSA, we always try to look at the variable temperature experiment to measure the CSA. So 100 Kelvin so far has been a nice temperature, because we can freeze most of the dynamics, and not what actually the question of earlier, that if we take a methyl group, it rotates, so we cannot freeze it. So we will have to do DNP maybe at helium temperature, then we may be able to see maybe this pi interaction. Maybe a nice project to do with people that does, helium NMR DNP, helium temperature DNP.
Okay.
Thank you. Thanks very much.
All right. Okay, so there don't seem to be any further questions, and we're now at 12:30 Boston time. Okay, so again, we'd like to thank Christophe and Daphna for really two very beautiful talks today. Very different topics, but really very interesting in both of them. And again, we will be back here in 2 weeks. I'm not sure we know exactly who's going to be speaking in 2 weeks yet, but we will announce that shortly. So again, Christophe, thank you very, very much. And Daphna, thank you very, very much too for some excellent presentations today.
Thank you very much, Bob.
We will see you hopefully in a couple of weeks. All right.
Yes, I'll be there soon. Bye-bye.
Bye.